All right, so here's the good news, bad news deal. The good news is it's Friday. The good news is you don't have any homework tonight. The bad news is we're going to try to talk about velocity, but I'll try and make it as exciting as I possibly can and as best I can. Okay, so as we go through this, okay, we're going to start with something that's relatively simple. We're going to take a trip to Kansas City. Okay, so we're going to go from Wichita to Kansas City. I'm going to turn around and come back. Now, and as we go through this, there are certain absolute rules that are set in stone, that are always, always, always true. Now, what I have to fight is that a lot of you have this preconceived idea of what you think is going to happen, right? And I'm going to tell you, this is what you're going to think, and don't think this, okay? Because it's just like you kind of come in with the stereotype that, well, positive velocity always means, going forward, and negative velocity always means you're in reverse and all this. So I'm going to try and dispel a lot of that. And I'm going to write the golden rule. Say, hey, no matter what, this is what always happens. This is what is always true. So bear with me. We'll get through this. Now, here's the reason why I'm going to spend so much time on this. It's because of the fact that literally, if you do not understand the subtleties of velocity, then you don't get acceleration. If you don't get acceleration, then you don't get forces. Okay? That's the basic idea. Now, as we go through this, when you look at velocity, and pretty much we're going to start off studying kind of constant velocity, okay? But in reality, velocity can only be one of two things. Your velocity is either changing, and that means that you're accelerating, or your velocity is constant. Those are the only two games in town. Okay, that's it. You're either speeding up, slowing down, or turning, or you're maintaining a constant velocity. Every problem that you're going to deal with in this class is one of those two situations. Either you're making something speed up, slow down, or turn, or it's at a constant velocity. Okay, that's it. You can't, oh, I'm kind of accelerating. No, you can't kind of accelerate. Okay, you're either accelerating or you're not. You're either at constant velocity or you're not. Those are the only two games in town. It's like, I'm kind of pregnant. No, you can't be kind of pregnant. Either you are or you aren't. You're either accelerating or you're not accelerating. That's it. Okay? Nothing else in between. So, here's what we're going to do. So, we're going to look at the great state of Kansas. Okay? And we're actually going to deal with three different towns. We're going to deal with Wichita. We're going to deal with Kansas City. And then we're going to deal with Winfield.
Sorry for the prairie.
Okay? Now, as we start this, what we're only going to deal with is one dimension at a time. We're not going to deal with circles and, projectile motion. We will eventually, okay? But now we're only going to deal with one dimension. So imagine, even though they're really not, but pretend that Wichita, Kansas City, and Winfield are all on like this big, massive number line. Okay? And we're going to start doing Wichita. Now, so we've established our frame of reference to be the state of Kansas. We need to pick a reference point. It could be Wichita, it could be Kansas City, it could be Winfield, it could be Pretty Prairie, it could be Dodge City, it could be Garden City, it could be Pittsburgh. Completely arbitrary. What do you want it to be? Okay, we're going to make Wichita the reference point. Okay? Lovely. Now, typically, your reference point is defined in numeric value because we're going to be talking about position. We're talking about where it is. Typically, your reference point is defined as being 0. It doesn't have to be. You can define your reference point as being 100. You can make it pi. You can make it negative 321.7. Doesn't make any difference. Okay? It is completely arbitrary. But what do you think would be easiest? 0. Let's make it 0. So we're going to define the position of Wichita to be 0. Now, because we're dealing with such large numbers, I'm going to work in kilometers. Okay? Because just because we have such large distances involved. Now, So imagine this is like a number line. Okay? Now, Kansas City is going to have a position. Winfield is going to have a position. Do you want Kansas City's position to be a positive or negative number? David, positive or negative? Pick one.
Positive.
Lovely. I'm going to assign the position of Kansas City to be positive 300 kilometers. Now, it's completely arbitrary. There's nothing magic that says, oh, everything over here has to be positive. That is not a golden rule. If David had said, I'm going to make that negative 300, it still would work. Okay? But typically, you all are in math classes and everything like that. You're used to numbers to the right being positive. Okay? So let's go with that. You don't, but you don't have to. If you wanted to be a rebel, oh, I'm a rebel. I'm breaking the law. I'm going to make this negative. Fine, you can do that. Great, you're cool. All right. But let's make it positive. David wants a positive. Now, that means that Winfield positions then has to be what, David? Negative. So I'm going to make that negative 100 kilometers. So I've got positive 300 up there, negative 100 down there. Beautiful, fantastic, we're grand. So I'm going to draw a chart because I like charts. Helps keep things organized. So, make a copy that says trip. Position initial. Position final. Displacement. Time. And velocity. So, go Wichita to Kansas City first. Okay, so it's Friday afternoon. It's 3 o'clock. You're bored. I've been to Wichita, you know, kind of got the back to school blues. You figure, okay, I'm going to take a road trip to Kansas City. So, fire up the car, get some buddies, some snacks. You always want to travel with snacks. Okay? And you're going to drive from Wichita to Kansas City. So, now, admittedly, as we start this is going to start off and it's going to be very, very simple. And it's going to, they're going, this is easy. Why are we spending a day on this? It'll get more complicated. Okay? So, here's the deal. We're going to go from Wichita to Kansas City. Okay? So, we're obviously going to move. We're going to have a velocity and all this good stuff. Now, if you're talking about displacement, what's the difference between displacement and distance? Elijah, which one is a vector quantity? Displacement or distance? You got a 50-50 shot. Displacement, good call. Okay? Because displacement is how far you go in a particular direction. Distance is just how far you go. Okay? And you'll see that's a big but subtle difference between the two of them. So, when you look at this, I'm going to start in Wichita, I'm going to end up in Kansas City. It's fairly simple, Elijah. What's my initial position? What's my final position? Okay, so I'm going to go over here and I'm going to fill that in. Okay? So, Elijah says, and says correctly, that x naught, my initial position, is going to be 0 kilometers. My final position is going to be 300. Now, displacement, and this is going to play out large in terms of any number of labs that we're going to do. It's very subtle, but it's important. Displacement is position final minus position initial. Okay, when we're talking about acceleration, when we're talking about velocity changes, it's always final minus initial. There's no exceptions. It's always final minus initial. So, in this case, and it's relatively simple, Mr. Baker, what's my displacement going to be?
300 kilometers.
300 kilometers. Okay? All right? Now, I want to go back to the map. So I'm going to go back to the map and I'm going to say, well, Elijah just told me that this is a vector quantity. Anything that's a vector quantity, Ms. Graber, has two things. What does it have? Anything that's a vector quantity has two components to it. Blank and blank. The first one starts with an M.
Mass.
Rhymes with magnitude.
Magnitude.
Magnitude. Okay? So it has magnitude, which is a fancy word just for a number, which we've already established that the magnitude of the displacement is going to be 300. Okay? So it also has magnitude and starts with letter D. Direction. Okay? Direction. True? So it's a vector, any vector quantity has magnitude and it has direction. Okay, got that? Kramer? Magnitude and?
Direction.
Okay. I'll ask you that again later on.
I'm gonna know it.
Okay. Yes. All right. So, that means that I can take an arrow and I can draw that up here. Oh, that is, oh, look, it's back. It's back just cool. Oh, now, look, the red line just up. Okay, so now I can draw this with an arrow because I need to indicate that it has
Direction.
and
Magnitude.
fantastic. So the magnitude is shown by the length of the arrow, right? Okay, and then which way it's pointing obviously indicates the direction. So from Wichita to Kansas City, there's a couple ways that I can express how I went. I can draw the arrow, okay, and that's going to point in that. The longer the arrow is, the greater the displacement is going to be. Okay, I can also calculate it and go, oh, that's 300 minus 0, which Mr. Baker emphatically stated is a positive 300 and life is grand. So there's a couple ways that I can show that displacement. I can do it graphically, I can do it mathematically. Okay, good, great, fantastic. Now, you get to Kansas City, and you get a phone call or a text message. Nobody actually talks on the phone anymore. They just use their phone to send text messages. So you get a text message that says, hey, Timmy's parents are out of town tonight. Big party at his place. It's like, whoa, cool. This is going to be epic. So at that point, you decide to turn around, and you're going to drive back from Kansas City to Wichita. Okay? You've been to Kansas City, had a nice road trip, you ate your snacks. Okay, time to turn around and come back. So we're going to go from Kansas City back to Wichita. Now, on the trip from Kansas City to Wichita, Courtney, what is my initial position?
Are we still keeping Wichita as a reference point?
Yes, once you establish that, you can't change it.
Okay, so I don't just
My initial position is 300. Okay? And what's my final position? 0. So what's my displacement? 300?
Or 0. Wait, no, 300. Right? 0, what is it? Negative 300? Yeah.
Are we good with that? It's a Friday. Okay? Negative 300. Are we good? Now, but Courtney actually fell for my evil trap. Okay? And this is exactly what you all are going to do. And you sit there and go, oh, Mr. Burkamp, we won't do that. You lie. Okay? You lie. Because Courtney's going to look at this and go, oh, I got 0 and I got 300 and I need to subtract them. I'm going to get an answer of 300. This is why you have to, and I beg of you, you have to pay attention to the fact that it's position final minus position initial. So our final position is 0, our initial position is 300. You subtract that out, and you get negative 300 kilometers. Now, let's talk about velocity. For the sake of argument, let's say that that took 3 hours. Okay? So on the way up, Paige, what's my velocity on the way up? 100, right? Because velocity is going to be my displacement divided by time. Okay? That's displacement divided by time. Velocity is not distance divided by time, and I'll show you why in just a second. Velocity is displacement divided by time. So in this case, I'm going to take 300 divided by 3, and I'm going to get 100. Okay, which is a pretty good clip. That's about 65 miles an hour. Okay? Now, on the way back, to make it easy, let's say that it still took three hours. So what's my velocity on the way back? Riley?
Negative 100 kilometers per hour.
Now, here's the first golden rule. Did I change direction to come back to Wichita? Did my velocity change sign? Yes. So here is absolute golden rule number 1. Whenever you change direction, the velocity has to change sign. Okay? No exceptions to that whatsoever. If you change the direction, your velocity has to change sign. So we're going to make a list of golden rules. Number 1, if you change direction, velocity changes something. Okay? There are absolutely no exceptions to this whatsoever. None. 0. Zip. Okay? No exceptions. Now, this is only talking about like in one dimension. Okay? If you're traveling in a circle, that's a whole other deal. But in one dimension, if you change direction, your velocity has to change sign. So if I take a little molecule here, and I throw this thing up in the air, does it change direction? Yeah, it would be real weird if it didn't, which means it would just keep going up, which would be cool, but not going to happen, right? So that changes direction. So what that means is that it could have positive velocity on the way up, then it would have to have negative velocity on the way down. Or if you wanted, you could define it differently. You could have it as having negative velocity on the way up, but then you can have positive velocity on the way down. I don't care, okay? It's completely arbitrary. But here's the deal. Anytime you change direction, your velocity, without exception, has to change sign. Now, as we go through this, and if you keep these golden rules in mind, you can take very, very complex problems and ask yourself, does it change direction? If you answer yes to that question, at some point your velocity has to change signs. No exceptions. Now, here's what you all are beginning to formulate. Okay? And you won't admit this, but I know that it's true. At this point, you're beginning to think, wow, if I go away from the reference point, I have positive velocity. And if I'm going towards the reference point, I have negative velocity. Because that's what we've established so far. Okay? That's what you all are trying, because teenagers and people in general like kind of like absolute rules. Like if this happens, this happens. Okay? Cause and effect. Okay? Going away from the reference point is positive, going towards the reference, point negative, whatever you want to know. No, that is not going to be a golden rule. Not going to be a golden rule. In this situation, it's true. Positive velocity is going away from the reference point. Negative velocity is coming back towards it. Okay? That, in this situation, that has happened. But I promise you, and you'll see why in just a second, that is not a golden rule. Okay? So right away, I want you to get out of your minds that positive velocity means going away from the reference point and negative velocity means going towards it. You cannot know that, okay? Now, here's another thing. That is not a golden rule. That positive velocity always means going forward and negative velocity always means going in reverse. No. Positive, negative has nothing to do with forward and reverse, okay? So don't think, oh, when you go home today and put your car in drive, oh, I have positive velocity. Oh, I got to back up. Oh, that's negative velocity, okay? No, it's completely arbitrary on how you set up your system. So let me say what is not a golden rule. What is not a golden rule, positive velocity is going forward, negative velocity is going in reverse. Okay? Not true. Positive velocity does not always mean that you're going away from the reference point. Negative velocity does not mean that you're coming towards it. Not golden rules. Okay? It might happen that way, but it doesn't have to happen that way. Okay? Good so far. And you're going, okay, well, this is kind of cool. Now, if I go back to the graph, now, this is my vector on the way up. So then I could draw my vector on the way down. I will go green. And I'm going to draw that coming down here like this. Okay, and another golden rule is that, like some vectors are always red and some are green. Color doesn't have anything to do with it. So, here's my vector going away, here's my vector coming back towards it. Now, you get to Wichita. And for whatever reason, there's a bunch of smoke in the car. I don't know why. Maybe there was an electrical fire, whatever. Okay? There's smoke in the car. And you miss Wichita. Okay? Like you completely miss every exit for Wichita. Okay? And then all of a sudden, the smoke clears, and you realize that you're in Winfield, America. Okay? And if you've ever been to Winfield, you know that, like, oh, Winfield. Okay, so now we need to look at the trip from Wichita to Winfield. Okay? So at this point, and let's go with the map. So at this point, we've gone past Wichita all the way down here to Winfield, America. It's like, whoa. So, Mr. Adam, I'm going from Wichita to Winfield. What is my initial position?
7 kilometers.
What's my final position?
Negative 100 kilometers.
Negative 100 kilometers. So what's my displacement?
Negative 100.
You sure?
No, positive 100 kilometers.
Well, which one is it?
It's positive 100 kilometers.
Why?
Because. No. It's initial minus.
No.
Minus.
It's always final minus
Okay,
initial.
negative 100 kilometers.
You sure?
Yes, I'm 100% sure.
Why?
Because we start at the initial. Because it is.
Because it is. Okay, Aristotle. We don't need proof. We just say because it is.
That's right.
What's my final position?
Negative 100 kilometers.
What's my initial position?
0.
What's negative 100 minus 0?
Negative 100.
Okay, so we're good?
Yeah.
Okay, all right.
We're all good.
Okay. All right. Now, so now we're going to look at the Wichita to Winfield trip. Okay, so now we're going from Wichita to Winfield. Now, Reed just established that my initial position is
0 kilometers.
0 kilometers. My final position is
Negative 100 kilometers.
negative 100. And he has emphatically stated that if I take negative 100 minus 0, I get negative 100. Now, let's say that that took 1 hour. Okay? Now, check my math, but if I take negative 100 and divide that by 1, I still get negative 100 kilometers per hour. Now, at this point, you need to notice something very, 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 very important. Okay? It's muy importante. Right? That's the extent of my Spanish knowledge right there. So, look what happened. I went from Wichita to Winfield. So if I were to come in here and draw that vector, that's going to be down here like this. Now, At this point, I'm now going away from the reference point. Okay? So initially when I was going away from the reference point, I had positive velocity. Now, then I said, well, I'm coming back towards the reference point, and then I had negative velocity. But now, I'm going away from the reference point. So why didn't my velocity change sign?
Didn't change.
Hayden, why didn't my velocity change sign?
Didn't change direction.
It's true. Okay? I'm still going in the same direction. So even though I went past the reference point, my velocity did not change sign because I did not change direction. So that's one of the things I want you to get out of your minds right now. Oh, I went past the reference point, my velocity is going to change sign. No! You're still going in the same direction. Your velocity is not going to change signs just because you went past the reference point. Okay? Because velocity is a vector quantity, which means it has
Magnitude of direction.
magnitude and direction, right? So I'm still going in the same direction. Therefore, I didn't change signs. Okay? And I'm still going at negative 100 kilometers per hour. So, when I look at this, okay, now I'm in Winfield. It's like, oh, it's Winfield, it's a Saturday or Friday night, Timmy's having a big epic party. We need to get back to Wichita. So at that point, Riley J, what are you going to do?
Change direction.
Which means your velocity has to.
Change sign.
Now, Riley, I'm going to go from Winfield to Wichita. What's my final position?
0.
What's my initial position?
Negative 100.
Perfect. Now, we're going to go back to here. So now we're going to look at going from Wichita to Winfield, America. Okay? Excuse me, I'm sorry. Winfield to Wichita. My bad. Was thinking. We're going from Winfield to Wichita. Winfield to Wichita. Now, Riley said my initial position is negative 100. My final position is going to be 0. Now, Abby, what's my displacement?
100 kilometers.
Why?
Because it's the initial minus the final.
Yes?
And so then change signs plus, it's positive.
With 2 thumbs up. Okay. Ashley, do you agree?
Yes.
Okay. Now, here's what, and Abby said it perfectly. Okay? Perfect. She said, all right, to get this displacement, I'm going to take my final position, which is 0, minus my initial position, which is negative 100, which gets me a positive 100. Now, here's what you're going to do wrong. Mark my words. This is what you're going to do wrong. And again, today, on August 22nd at 8:20, you're going to go, oh, Mr. Burkamp, we'll never do that. You lie. You're going to look at negative 100, you're going to look at 0, and you're going to go, oh, my displacement is negative 100. Okay? Because you're going to forget all about that it's position final minus position initial. Okay? Trust me, this is what you're going to do. And you go, no, we won't. Yes, you will. Pay attention to that, though. Now, let's say that it took 1 hour. So now my velocity is positive 100 kilometers per hour. Now, look at what Riley said was going to happen. I got to Winfield, I changed direction, right? When I changed direction, therefore my velocity had to change sign, right? Simple as that. Now we're back at Wichita. Now, here's what I want you to notice in terms of the difference between vector quantities and scalar quantities. 100 kilometers per hour is about 65 miles per hour. Okay? Now, if you're driving and you have a speedometer in your car, okay? You have a speedometer. Is your speedometer going to tell you that when you hit Kansas City and turned around and started driving back towards Wichita, is your speedometer going to go, oh, now you're going negative 65 miles per hour? No. The only thing it's going to tell you is that it's going 65 miles per hour. Your car is not going to tell you which direction that you're going. Okay? It's not going to happen. So that's why we call it the speedometer. So if all you know is you're going 65 miles an hour, that's just a number. That's just the magnitude. You have to have something else to give it the direction to make it velocity. So velocity is just basically speed with the direction. That's all it is. Now, when you look at your odometer, what does your odometer tell you?
Miles an hour.
Yeah, how far you've gone, okay? That's all it does. Your odometer just tells you how far you've gone. Your odometer tells you distance, okay? Now, look at this. On this trip, what's the total distance traveled? Sydney, what's the total distance traveled? Beautiful, 800. Why?
Because you're not going there back, go from Kansas City back to Wichita, that's 600, and then you, this truck signature, you go back, which is 200.
Perfect answer. Okay? Perfect. So your car would tell you that you traveled 800 kilometers on this trip. You had 300 up, you had 300 back, you had 100 down to Winfield, and then you had 100 back. So your total distance traveled would be 800. So that's going to be my distance. 800 kilometers. Now, this is where this is going to get just a little bit weird. Okay? Not bad, but just a little bit weird. For the entire trip, okay? For the entire trip, what's my final position? Ashley, what's my final position for the entire trip? What's my initial position for the entire trip? So what's my total displacement for the trip? 0. So my entire displacement for the trip is 0. And you're going, whoa, what do you mean 0? We drove to Kansas City. We drove back to Wichita. We passed Wichita. We ended up in Winfield. Almost got beat up. We had to flee for our lives and get back to Wichita. Okay, I threw that part in. So what do you mean my displacement is 0? But when you look at displacement, okay, when you look at displacement, because it's position final minus position initial, your overall displacement for the trip is 0. Okay? Now, overall, what's my average speed for the trip? Daniel, what's my average speed for the trip?
Like 100 kilometers an hour.
Why?
Because you go 100 kilometers an hour.
Well, what's my total distance traveled?
Oh, because you went 800 kilometers and then it took you 8 hours.
Yeah, it took me 8 hours. So my average speed, okay, my average speed is 100 kilometers per hour. Okay? Now, this is where this is going to get a little bit weird again. To get my average velocity is my total displacement divided by time. So what's my average velocity? 0. And you're going, whoa, Courtney's going. Okay? Right? Like this early on a Friday morning, you're going to tell me my average velocity is 0? Yes, it is. And you're going, but I was moving. You know, I drove all this distance. I spent 8 hours on the road. Okay? I almost got beat up in Winfield. Come on, seriously, this is a real life adventure. What do you mean I don't have? It's like, true. Mathematically, your average velocity is 0. Now, I'm not saying that you didn't move. I'm not saying that, you know, Bubba in Winfield didn't come after you with a shotgun. That's not what I'm saying. Okay?
It's different.
I'm not saying you weren't there. I'm not saying you weren't in the Flint Hills and almost hit a deer on the way back. I'm not saying that. Okay? All we're saying is that your average velocity overall is 0. Okay? And if you think about it, well, you spent 3 hours with a positive velocity, you spent 3 hours with a negative velocity, then you had another hour with a negative velocity, then you had another hour with a positive velocity. Overall, it adds up to 0 in terms of an average. Okay? Now, this is another situation where I want you to look at this and go, when you look at this velocity vector, when we're going from Winfield to Wichita, if you notice here, if you want to color code that, that would be back in red. So this is a situation where I have a positive velocity, but I'm going towards the reference point. Okay? So here I had positive velocity, I was going towards the reference point. Here I had negative velocity, I was going back, or excuse me, away from the reference point and then towards the reference point. But then I went past the reference point. Well, my velocity still stayed negative. But now I have positive velocity because I'm going in that direction. So whether it's positive or negative doesn't have anything to do necessarily with where you are in terms of the reference point. So just because I tell you that I have a positive velocity, you cannot tell just by that information where I am relative to that reference point. Okay? The only thing that you can tell is which direction am I moving. So basically, no matter where I am in terms of that reference point, if I'm moving like to the right, I have positive velocity. If I'm moving to the left, I have negative velocity. And where I am in terms of the reference point, you cannot tell. So if I tell Brett Moon that I have a positive velocity and I say, hey, where am I at in relation to the reference point? And I asked him that question, he'd go, I can't tell you. He would not be able to tell me. The only thing that he would know is that I'm moving in a particular direction. That's it. Okay? Got it? Good. Okay. Stop that. You've been sitting for a while. Stand up.
Oh no.
Okay, he's sitting there on 3 legs. What, did we have an earthquake?
It created a vacuum when you ran so fast it kind of sucked everything.
And then there was a time delay until it got there.
Yeah. This is,
The camera just fell over.
I'm pretty sure they saw that. I'm pretty sure they
Yeah,
saw
I was
it.
ever seeing the chemistry book getting real close at that point.
No, it fell this way.
Oh, it fell backwards.
oh, that doesn't make
Okay,
sense.
well, we're going to see the ceiling then. Okay. All right. So, my position final is what? Addie?
-4.
Position final.
Oh, position final.
Because it turned it.
-2. Minus an initial position of
2.
2. And that took 1 second, which means my velocity is
-4.
-4 meters per second. Wow, impressive. Okay? Now, did my velocity, Sydney, change sign? Which means that beautiful, because I was initially going this way, right? I stopped for dramatic flair. In a bolt of athletic prowess, I went from +2 to -2 in a stunning 1 second. My velocity changed, therefore, what had to also change?
Sign of your.
Sign, because I went from positive to negative. Now, did I go past the reference point?
Yes.
Mr. Baker, I went past the reference point. Why did not, since I went past the reference point, why didn't my velocity change sign?
Because it only changes sign when you change direction.
That's right. Just because I went past the reference point doesn't mean that my velocity is going to change sign. Okay? Beautiful. Now, what do you notice about the steepness of that line? Which means that I'm moving faster. Because if you view velocity as being a rate of change in position, the steeper the line, okay, in this case, the faster my velocity is going to be. Now, when you talk about velocity, and I have to dispel this because math world has kind of got you guys screwed up. If you're in a math class, okay, if you're in a math class, okay, this is important. Forget that you're in a physics room. You're in a math class, okay, right? Everybody kind of starts this nervous twitch. Yeah. Okay, so you're in a math class, and I ask you, which one is greater? +1 or -4? +1. Would you all agree that positive 1 is greater than negative 4 if you're in a math class?
Yes.
Okay? Now, I have to dispel this from a physics standpoint. If I ask you which is greater, negative 4 meters per second or a positive 1 meters per second, what would you say?
Negative 4.
Negative 4, because the negative sign just indicates a particular direction. Here's the classic example, okay? And everybody says, oh, in math world, you always say, well, positive 1 is greater than negative 4. Okay, let me ask you this. I can hit you with the bowling ball, okay? It can either be going negative 400 meters per second or 1 meter per second. Which one would you pick? The 1, okay? Right? So the negative 400 in the math world, oh, that's a very small number. Negative 400 meters per second is going to be really, really fast, especially if it's a bowling ball, because it's going to be going faster than the speed of sound, which would be really, really cool. So when you're comparing numbers in physics between like a positive 1 and negative 400 meters per second, what was this?
I was talking about the impact on your face, and if you did it in slow motion, you're just the ripples, and then next thing you know, you're screaming.
Yeah, with the bowling ball faster than the speed of sound, it's just not going to end
Your
well.
head's gonna.
It's no. Okay, I didn't even think about it. Okay. So when you're talking about a velocity, do not get wrapped up into the math definition of greater than and all that good stuff. Okay, so let's say that I'm over here, right, and at this point I'm going to saunter. Okay? Saunter. Very slowly, very slowly, very slowly. Back to the reference point. Okay? That was a nice saunter. Thank you very much. Okay. All right. Kind of a 60s thing. No. Can't do that. Saunter. Okay, saunter. Now, so let's say that because I had such a blazing speed from here to here, I got to saunter because I got to conserve some energy. Okay? So that's going to take me, I'm going to go from negative 2 all the way to the reference point, and let's say that's going to take me 4 seconds to travel 2 meters. Now, Courtney, is my velocity going to change sign? Why? Because I changed direction. Now, ask your esteemed partner to verify this. Okay? So, what's my final position? 0. Ask Courtney. You're just there to verify your answer. Okay? If my final position is 0, what's my initial position, Courtney? What's my displacement? Why? Right. Because if I'm looking at my displacement, I'm going to start at negative 2, I'm going to end at 0. Right? So, displacement is what minus what, David?
Final minus initial.
Perfect. So my final position here is going to be, my final position is going to be 0. My initial position is negative 2. So I'm going to have 0 minus a negative 2 meters. That gives me a positive displacement of 2 meters. That took me 4 seconds. Therefore, my velocity is half a meter per second, which means this line here is going to be the most shallow of all of them. Okay? Because this is my slowest velocity. So, in all of these situations, notice that I have straight sloping lines, which indicates that you have constant velocity. How do you show an object that's at rest? Elijah? How do you show an object that's at rest? Horizontal. I was hoping for that. Okay, yeah, there you go. Okay? All right? So, you're moving, you're at rest. You change the direction. You know that you changed the direction because the object, because the slope changed. Sign. Now, true or false? Just because the slope changes, that also, if the slope changes, that means that you also change direction.
No.
Yeah, because let's say that you had a position time graph that looks like this. Okay, so here's the position time graph. You got this action, and then you got this action, okay? So here's 0, here's like -4. So if I just said, if all I gave you was that position time graph, here's 0, okay? What would that object do? Mr. Baker.
Well, it would like start off kind of slow, then it would get really fast, and then it would be at rest.
Would I go past the reference point?
Yes.
Did I ever change the direction?
No.
How do you know?
Because the slope is positive the whole time.
Beautiful. I have a positive slope the entire time. I did not change direction. Okay, what's the only way that I could show a change in direction, Miss Swanson?
Change direction, or changing the slope.
So if I brought it down like this, would that show a change in direction?
Yeah.
Yes. Okay, got it? Good, fantastic. All right. Now, I just want to start in on velocity time graph, so shut that down for a second. On Monday. But this is a velocity time graph. Okay, similar to a position time graph in the sense that time is still on the x-axis, which it always will be. But now instead of having position on that y-axis, I now have velocity on that y-axis. So imagine that you're driving your car, and instead of like the sports package, you got the physics package, okay? Which means that your speedometer, instead of showing in miles per hour, you have one that reads in meters per second, okay? Because you're just that cool, right? Because he's like, I'm a physicist, I want to show in meters per second. Okay, so you're driving, and Dan is with you, she still happens to have the stopwatch, okay? So Dan is going to keep track of time as you're driving. So you're stopped out in the parking lot, there's a break in the traffic, at time 0, you're going to start at 0 meters per second. Do you think you always have to start at 0 meters per second?
No.
No, it can start at anything, okay? There's nothing magic about starting at 0, but we're going to let this one start at 0 meters per second. Does that mean, and listen to me very carefully before you answer this question, I'm going to start at 0 meters per second. Does that mean that I'm starting at the reference point, since I started at 0 meters per second? No, categorically no. All you know is that I'm starting at 0 meters per second. I can be over here, I can be over there, I can be in Moscow. All I know is that my velocity is 0. Okay, where I'm at, I don't know. All I know is that I'm starting at 0. Now, I press down on the gas, right? And Danny tells me that after 2 seconds, I'm going 6 meters per second. So here's 0, 0. Here's 2 seconds. There's 6 meters per second. Now, you're in a math class, not in a physics class. Okay? Ashley, what's the slope of that line? You're going from 0, 0 to 2, 6. What's the slope of that line?
3.
3. Now, if you're in a math class, you're golden, right? You said 3, and that's all you'd have to say. But we know what the axes are. So let's look at what you did. You took 6 meters per second minus 0 meters per second, and you divided that by the time of 2 seconds minus 0 seconds, right? Now, notice when we had a position time graph, we had position final minus position initial. What do you think we have here? We have
Velocity.
minus,
Velocity initial.
which is going to be shown as V minus V naught. Okay? So just like displacement was position final minus position initial, which is x minus x naught, this is going to be V minus V naught, velocity final minus velocity initial. See the same pattern. Now, I'm going to divide that by time. Oh, miracle of miracles. Now, Garrett, when I take 6 meters per second and divide that by 2 seconds, I get 3. Okay? Because Ashley said the slope is going to be 3. Math definition, the slope is 3. Physics definition, what units do I end up with?
Meters.
Meters? Everybody cool with meters?
No.
No, don't get caught with meters. You're taking it's meters per second per second. Your velocity is changing. Otherwise known as
Acceleration.
acceleration. So the correct units are,
Squared.
yes, meters per second squared. The seconds don't cancel out. Multiply by the reciprocal. Okay? Now, so Gary, since we end up at meters per second squared, the slope represents
Acceleration.
perfect. Now, so golden rule. The slope of a velocity time graph gives you
Acceleration.
Distance.
so the slope of a velocity time graph gives acceleration. Okay? No exceptions to this whatsoever. Okay? Now, don't sit there and start to memorize this. You can if you want. Okay? But if I give you this question on a test, which I promise you I'm going to, I promise I'm going to ask you this. The sun's going to rise in the east. I'm going to ask you what the slope of a velocity time graph gives you. Okay? I promise this is going to happen. And let's say you're on the test and you flip out and you go, oh my God, I don't remember what it represents. Look what happens with the units. Okay? You've got meters per second divided by seconds. Okay? It's meters per second per second. It's the rate at which your velocity changes. Now, look at the big picture. Okay? Understanding science isn't about memorizing facts. Okay? It's looking at a pattern. If you had a position time graph, the slope gave you the rate of change in the position as a function of time. It was meters per second. Okay? If it's a velocity time graph, okay, if it's a velocity time graph, then the slope is going to represent a rate of change in your velocity as a function of time. Okay? So if it's a position time graph, you're looking at position changing as a function of time. If it's a velocity time graph, you're looking at velocity changing as a function of time. Okay? Now, it isn't, but let's say the slope had worked out to be meters, but let's say it isn't. If the slope would work out to be meters, what would the slope represent? If it had been meters.
Velocity.
No, if it had just been meters.
Oh,
Yeah.
distance.
If it had worked out to be meters, we would say the slope represents distance. But it doesn't. The slope represents acceleration. Now I want you to look at something very important. I'm going from 0 up here. Am I speeding up? David, am I speeding up? I'm going from 0 to 6. Am I speeding up? Yeah, I can't go any slower than 0. Okay? Freshmen can't go slower than 0. Okay? If you're at 0 meters per second, that is as slow as you can go. You cannot go any slower than 0. Okay? No, what if you're going backwards? No. Okay? You can't go any slower than 0. So, you notice this line is coming up like this. Now, pretend that you're in a math class. Courtney, all I want is the sign. What is the sign of any line that comes up like this? Is the slope positive or negative? Now, we just established that the slope represents acceleration. Notice that I have positive acceleration, and I am up here, so I have positive velocity. David just said I'm speeding up, okay? Which I am. So, we'll talk more about this, but here's one of the things. Anytime you have acceleration and velocity that have the same sign, you have to speed up. Okay? Now, the other way that you can look at this is that you're moving away from 0 meters per second. And since 0 is as slow as you can go, if you're going away from 0, you have to be speeding up. Now, what if I brought this line down like this? Would I still be speeding up? Yeah, because then I would be going away from 0, but then I would have negative velocity. Okay? All right, I'm done. Have a good weekend.
Acceleration right now.